A hash-based message authentication code, abbreviated as HMAC, is a message authentication code constructed on top of cryptographic hash functions and as a system allows to verify the integrity of a message based on MAC tags associated with the message and relative to a symmetric key. With this, it's a system that allows a recipient to verify the source of information if the symmetric key used is known to only be available to, for example, the recipient and exactly one communicating peer. If either the message was modified, or the wrong key was used, or a wrong MAC tag was received, or a wrong hash function underlying the HMAC is used, then the HMAC verification process will fail and the message received should be deemed as not authentic. The following demonstration will show how HMACs can be used in Python and how the behavior of HMACs can be explored in case of the different error scenarios. To demonstrate the use of HMACs in Python, I started with outlining the necessary steps required for using an HMAC. For this demo, I opted to use HMAC SHA-256, which has SHA-2 with 256-bit hash values as the underlying hash function. The message used is again just a byte string with the name of this course. Then a symmetric key is required. With HMAC SHA-256, a key of at most 512 bits is recommended, but here I decided to go for a randomly sampled 256-bit key, which is assumed to be secure. Then I constructed the HMAC SHA-256, for which I had to get hold onto the SHA-256 hash function, which can be found in the cryptography library inside the hashes module, and with SHA-256 and the symmetric key at hand, I could then construct the HMAC SHA-256 object by using the HMAC class from the cryptography library HMAC module. Then it was time to calculate a MAC tag for the message and to verify that this MAC tag for the original correct message and under the correct symmetric key indeed verifies as a correct MAC tag. This was the demo of the happy path within an HMAC system, and it was time to investigate the error scenarios. The first error scenario was attempting to verify the MAC tag with a now modified message. The second error scenario was attempting to verify the MAC tag with a different key than the key used to calculate the MAC tag. The third error scenario was attempting to verify the message with a wrong MAC tag. And the fourth error scenario was attempting to verify the message and MAC tag with a wrong HMAC using a different underlying hash function. Going into the first scenario, setting up a wrong message and an attempt to verify it results in an invalid signature exception, thus showing that this error scenario is indeed properly detected by HMAC. Wrapping this into a try except clause that asserts that the exception was indeed thrown, then had the program running again and verifying that the exception was indeed thrown. The investigation of the remaining three error scenarios was the same, indicating that each of the error scenarios is indeed detected by HMACs, with the responsibility of properly dealing with each error scenario then of course being delegated to upstream clients of the system. This concluded the demonstration of how to use HMACs in Python, which is a cryptographic primitive allowing for the verification of the authenticity of messages and data received.